Hello everyone. Welcome back to the third and final webinar of the launch of our new version. You've all been extremely generous in your praise of Comosys, and the interest which the webinars have generated is truly amazing. It's pretty clear that you're liking what you're seeing, and that really makes me happy. So this will be the last of the series of 3 webinars which we had planned for the launch of the new version, but it won't be the last time we meet. We will continue to provide interesting presentations for you regularly, but we will make sure to keep them short and manageable. We are planning a weekly series of webinars, which could last anything between, say, 10 to 15 minutes, something you can watch without cursing me for making you wait so long. In fact, hopefully something you can look forward to every week. They'll be short and focused on one or two specific topics. You can even consider them to be little Comosys training webinars, mixed with interesting observations about whatever it is that we're doing. Basically, they'll be good fun, not like the marathons we were forced to organize in these last 3 weeks. Now, typical full training of Comosys covering the analysis, design, steel detailing, concrete and rebar detailing, etc., that takes about 60 hours. And we've tried to put a fast-paced summary of all that in 6 hours in these 3 webinars, in such a way that the experienced engineers and detailers among you will actually pick up a lot just from these 6 hours if they watch the webinars carefully. So while these webinars are not replacements for formal training, they've been designed to be like a quick startup guide for someone who's sharp and interested. The details, of course, can come later. So I would like all those decision makers who are interested in Comosys to request their engineers and detailers to actually watch these webinars a few times. It'll be even better if the decision makers themselves also spare a few hours from their busy schedules and watch this condensed training. These 6 hours will save your company thousands. So I think it'll be a good investment. I want you all to not feel hesitant simply because your teams haven't received formal training yet. Comosys is very intuitive to learn, and your teams and our teams are also here to help you just in case you get stuck. Now, let's get back to today. I'll try to keep it around 1 hour, but you know me. By now, I usually end up not keeping such promises. Anyway, let's get to the point and start our webinar. As you know, the main thrust for today are the analysis and design capabilities of Comosys. Once again, I will try and take you through the various steps involved in this process. I've created a little outline for myself, and I'll try to make it as useful as I can for you. So let's start with the basic element entry. And on the top, as you know, we have these menus, and we'll be talking about the steel and the concrete menus and the analysis and design menus today mostly. So if we come to the steel menu, you have over here your basic frame element entry commands. And you might be thinking that in normal typical analysis programs, you have basically one command to enter frame elements. You basically select 2 points and you keep entering your elements. But in Comosys, you've got 1, 2, 3, 4, 5, 6, 7 commands to enter, and there are actually even more beam groups. These are all beam groups, by the way. So there's a column beam group, there's a beam group, this is a horizontal bracing group, there's a vertical bracing group, truss group, purlin groups, and there are other groups as well. But the reason why we have these over here is because we want to automatically facilitate filtering and some other technologies which we've discussed in the other webinars like IntelliConnect and this and that. Now, so coming back to the analysis part over here, to enter elements, all of these commands basically work by selecting 2 points, except for the column, which works by selecting a single point. So if I were to select this column command and press any point, click on any point, immediately a column is created. It doesn't require 2 points. The reason why it doesn't require 2 points is because it takes the current work plane Z direction as the direction of the column, and the length of the column depends on if I double click on this column right now, then there's a parameter over here. This is the point which I selected. How much does it want the column to go below that point, and how much does it want the column to go above that point? So these two numbers basically define the exact position of the column. And like I said, this direction comes from the z-axis of the current work plane. So if I were to, for example, enter 1000 over there, it will extend the column 1 meter below the point I selected. And you can choose according to whatever your needs are. So now let me quickly enter a few more columns using the same command which we just talked about, and then go to the beam command. And then basically this one takes 2 points rather than a single one like the column. And we can basically create some beams on the screen. Now, as you can see on the screen, I have immediately started benefiting from using different commands for each beam group. So not only are the beams of a different color, and visually I can immediately tell which ones are the beams and which ones are the columns, but if I were to make a general selection and press enter, I can even see that beam grouping over here. So if I wanted to select only the beams, I could just double click on the beams and only the beams would then get selected. Now, if the benefits of that automatic grouping weren't clear in the simple case which I just did, let me just show the same thing to you in this large preheater model. Let me just go and select randomly like that. But what if I wanted to select only the horizontal bracings on the floors? I would just press enter, go to my profiles and group by beam group, and I say I want the horizontal braces only, and immediately my horizontal braces would have gotten selected. This could be further refined into just what a particular section or the beam group, but the point I'm trying to make over here is that this automatic grouping by beam groups is extremely beneficial, and I would recommend that you never, what you can do is, for example, use the beam command to enter the entire building. You can do that. There's nothing stopping you from doing that. But make it a habit to, in Comosys, to always use the different commands which we have over here for the beam groups. The reason why they're grayed out right now is because the model is locked, because this is an analysis model. But the point is that you always use the relevant command, which if you're entering a vertical bracing, use the vertical bracing command. If you're entering a horizontal bracing, use that, a truss, a purlin, a girth, depending on your need. Now, coming back to our small building, let's add a few more beams. So let me just go from here to here, from here to here. As you can see, I've just snapped to the midpoints of these existing beams, and so what we have over here are the snap options, and if I turn them on, you can see that the midpoint has been turned on, and you've got other things like control points, intersection points, perpendicular to, perpendicular from, parallel, etc. Different options are available. But when we say midpoint, what we mean is the midpoint of a segment, actually. So this was the original beam, and when I was entering this beam, I was snapping to the midpoint of this original beam, and I went from there to there. But now if I go to the beam command again, I come over here, there's another midpoint which comes up, and this is now the midpoint of this section of the beam. So what midpoint will basically tell you is that it is always the midpoint of the segment. So I can go like that, I can go from here, and this one will snap perpendicular, it's also the midpoint, and I can go from here to here, and it will snap from the middle of there to the perpendicular point at the other side. Now, one thing which I want to say is that if I zoom in there, for example, and I wanted to enter a plate, just like you can see that I can snap to any one of these points like that. All those are snappable points. But if I were to enter a beam, then those points it doesn't snap to those points, because it wants me to snap to the finite element endpoints rather than, because I could be very far. I could be working from this zoom level, and I could just go in there and say, okay, I want an element from there to there, and accidentally I could have chosen maybe this point when I was doing that. So by default, Comosys will not allow you to snap to these definition points, or rather not to the definition points. We call them control points of the members, but it will force you to snap to the definition points. Now, of course, you can override these options, and you can snap anywhere you want if you needed to. But the good thing is that it will not allow you to make mistakes like that unknowingly. Now, since we're talking about finite elements today and analysis and design, we have to talk about nodes or joints as we call them in Comosys. Now, in Comosys, you don't create nodes separately and then connect elements to them. As you create your elements, your nodes are being created automatically. So if I were to zoom in there, you see this yellow dot over there, this one, which you can select. That's a finite element node. And you have the visibility and selectability of that over here. So if I can turn them off, I can turn them back on. But the moment you create any element, so let me create a column, for example, over here. Immediately, if the nodes at the two ends are also created with it. So there's one over there, and there's one, if I were to turn it around, there's one over there as well. Now, the thing about these nodes is that they're of two types. One what we call end nodes, and one what we call intermediate nodes. If the node is an end node, it will be yellow. So this one over here, for example, was created when we created the column. But then when we entered the beams, the beams did not create extra nodes over there. So they're not three nodes over there. Only when the first column was entered was a node created. When the beam was entered, it automatically, the program noticed that the node already exists at that point. So I don't need to create a new one. So I just use the old one, and the same for this one. So if I were to double click on this node, you will see that it says it has a number of connected frames to be 3. If I were to double click on the column I just created over there, you will see that the connectivity will be just 1. Or if I were to, for example, create a beam from there to there and zoom in again, and now double click on this one, now it's turned into 2. So the connectivity keeps changing as you keep entering new elements. Now, I was mentioning that there are two types of nodes. One is the yellow one, which we call the end nodes. And what we mean by that is that if a node is yellow, what it means is that all the elements, so the connectivity is 3, which means 3 elements are framing into that node. But the fact that it's yellow is telling me that all the elements are the end. It is the end of all the elements framing into it. So it's the column end over there. The beam ends at the same point, and the other beam ends or starts at the same point, basically. But these nodes can also be blue. So, for example, the same node over here is blue, and this one has a connectivity of 2, which means that there are 2 elements. One is this one, this continuous one, and this beam framing into it. Now, the fact that it is blue is telling me that this is not an end node, but it is an intermediate node. And what that means is that from the connectivity of whatever 2 or 3 or 4, from that connectivity count, one member is continuous and the others are ending at that point. So in this case, the one member which is continuous is this beam, and the others might be. So if I had another beam, for example, from here to here, now if I double clicked on that, the connectivity would be 3. But still, the same one, this one would be the one continuous one, and the other 2 would have to be end points. So if one of the elements is continuous, the node will turn blue. But if all are ending or starting at the same point or at that point, then the element will be yellow. Now, what you're not allowed to do is something like this. So, for example, if I were to say, let me find an example over here. Yeah, maybe I can do something like this. I can create a beam from here to here. Now, this one actually is going through this point over here, but there's another one going through this point as well. So you can't have 2 elements which are continuous at the same point. If you have that situation, you have to find another solution. You have to break that element at that point and re-enter it from the other side. Now, that might seem obvious. It makes sense that you shouldn't have 2 continuous elements going through the same point. Obviously, there'll be a huge clash. But in steel detailing, you can have situations like this. So, for example, if I were to go to the midpoint from there to there, and instead of putting that to be behind, if I entered it like that, now this could be a valid real situation in which this beam is sitting on top of these beams, and in this case over here, one beam is going over. So at this point, there is a continuity in both the elements. And if I were to go to my finite element model, which I can do by pressing Alt D by, for example, a couple of times, I can see the line mode. You can see that this line is continuous as well as this line is continuous, but no node is formed over there because right now they're oblivious to the existence of each other. They don't know. This one doesn't know this one is crossing over me, because only one node can be continuous. And if you have a situation like this, what you would need to do is you would need to actually slightly raise this and give it an offset and then connect it so that then have these little connection elements between the two, and those connection elements will then create the relevant nodes. Right now, if you do the analysis, this one and this one will not have this contact at this point. Another thing which I can mention over here is these little green dots which you're seeing on the screen. They represent internal releases. So if the element has any release, so for example, if you're talking about this beam has a start and an end, and we can see that there is some release at the start and there is some release at the end. Now, what release that is, we don't know. We have to double click the element and go to the analysis tab over there. And there we see that the start has moment M22 and M33 releases, and the end has M22 and M33 releases. But even if it had some other release, as long as there was one release, you would see this green dot. And there's a toggle especially created in Comosys, because in steel, it's extremely common to have these M22 and M33 releases at the ends. So we have a toggle called Control R, which we can then do to remove those M22 and M33 releases. And this is very commonly used in steel. Now, it's a good practice to remember this blue and yellow color coding, that the blue ones are intermediate ones and the yellow ones are end ones. Because if I make a mistake in snapping, that can remind me of my mistake or correct me when I make that mistake. So let's say I was entering a beam from here and I wanted to snap over here, but forever I'm going to make the mistake deliberately over here. Instead of snapping to that point, if I just press enter and I say dx1, which is just 1 millimeter away in the x direction, and I create a beam. Now, it seems as if, because from this distance, it seems as if everything is okay. But immediately, the presence of this yellow node will tell me something is wrong, because this one is continuous. And had I properly connected to this one, this should have turned blue. But since I snapped to about 1 millimeter away from that, it's actually yellow right now. And if I were to go into the plan view and turn on my finite element mode and I zoom in, I will soon see that actually I'm not touching that element. Now, one thing which needs mentioning at this point is that if you were entering a concrete building, for instance, and you were in this menu, and these are the commands which we typically use to enter the main parts of the building, and then we have some more on the side. But what I want to mention at this point is that only the beams and the column commands will actually create a finite element model. For example, if I were to create a slab over here right now, this will not convert into a finite element model. This does not mean that this is a shell element which will get converted during the analysis stage. Or if I were to create a wall between these two columns, this does not mean that this is a shear wall. Both these elements are merely for detailing purposes. You can do anything. You can create flares in them. You can modify their geometries any way you want. The primary purpose is for detailing. If you did actually want to convert them into a finite element model, we will talk about that. There's a different command for that, which we call supershells, and they're very nice tools where you can convert any shell or any slab or any wall into a supershell. But that's a separate thing which you would need to do. At this point, what I would like to mention is that merely seeing a slab or a wall over there should not tell you that this will become part of the finite element model. Now, a few quick words about creating load cases and load combinations in Comosys. So if you go to the analysis and design menu, you have your this menu item over here, or this toolbar. And you can, if you open that, you see there are several options in which you can create and edit load cases and load combinations from here. You can create and edit analysis cases. You can create spectrum functions. You can edit time functions and ground motions. You can have an automatic, this is very useful, this is an automatic load combo generator. And you can basically copy your load cases and combinations between models as well. So if I quickly go to the create and edit load cases and load combinations, I have several ones already created over there. And if I click on any one, you see that it has a name. This is a load case. You can give it a name. You can give it a type, which is a load case. Load cases can have types, and the types can be dead, live, wind, snow, earthquake, equipment, crane, construction loads, roof life. There are several cases which are typically used, and you can even add some customized ones if you want at the end. So every load case you will create will have a load case type. So let's go to, for example, a wind load case over here. And so these wind case load cases will have the type of wind load. Now there are certain parameters over here called state indices and substate indices. These are for cases, these are for things like moving loads. For example, if you wanted to create moving loads, you could use state indices and substate indices. And there are separate videos available which you can follow. But the basic idea is, so you can also use them, for example, for wind loads if you would. They haven't been used over here, but if you wanted, so if we could give wind x a state index of 0 and a sub index of 0 as well. But wind minus x, we could give a state sub-index of 1, and wind y, we could give a state sub-index of 2, and wind minus y, we could give a state sub-index of 3, for example. Now, what this will tell Comosys is that so wind, all the wind cases have a state index of 0, but their sub-indices are varying from 0 to 1 to 2 to 3. What that will tell is that when you generate the automatic load combinations, it will never put wind x and wind minus x together. They're all of type wind. It'll never put wind x or wind y together because they have separate sub-indices. Anything with a different sub-indices will be put in a different load combination. Similar things you can do with your earthquake, x, y, minus x, minus y. You can give them sub-indices if you want. And more importantly, for moving loads like crane loads. So if you have 2 cranes in your hall, for example, you can give crane number 1 a state index of 0, and then all its positions along the hall will have variable sub-indices. And the second crane will have a state index of 1, which will be different, and it will have its own sub-indices as far as its motion along the hall is concerned. So what Comosys will do then, it will combine, it will now put the first crane in 2 places at the same time, but it can put the first crane and the second crane in the various combinations of all their sub indices, and that's a very powerful feature which the load combo generator uses. Similarly, over here you have load combos where you can create as many load combos as you want. You can, like I said, you can automatically generate them as well, and there are separate videos which are talking about that. You have response spectrum cases where you can create as many response spectrum cases as you want. You can give them any modal combination of absolute sum or square root of sum of the squares, or CQC, complete quadratic combination. And you can also give them a directional combination in cases where you want the earthquake to strike from 2 directions with different parameters at the same time, and you want to tell the program how to combine those cases. Similarly, you have dynamic load patterns over here. So this is the area basically where you will enter your load cases and your load combinations. So we talked about load cases and how the load cases can have these state sub-indices. So we talked about the wind load case, which I've given the sub-indices of 0, 1, 2, and 3. And similarly, the earthquake ones I've also now defined as 0, 1, 2, and 3 for the sub-indices. And there's a crane load as well over here, which has 2 states. I mean, this could have 100 states. You could have a crane moving placed at, say, 100 different locations along the hall, and each one of them will become a load case. and you could very quickly then assign them these sub indices if you wanted to. But the point I'm trying to make is that once you define these load cases, and I've deleted all the load combos from here, because I wanted to show you the automatic load combo generation. So the load cases have been defined with the appropriate state indices. We've got self and dead and live. Then we've got wind, which has 4 states, earthquake, which has 4 states, and crane, which has 2 states. Now let me go to the automatic load combo generator. So if I go to the load combo generator, you see over here that on the left hand side you have options of choosing a standard, and whichever standard you choose, the load combination, the generic load combinations of that standard appear on the screen, and you can then turn all of them on, or some of them on or off, or depending on what you want. You can say, okay, I only want these or whatever. What I'm going to do is I'm going to go to AISC This has these basic 6 load combinations: dead plus dead as one, then there is dead plus live, then there is dead plus wind, then there is dead plus live plus wind, and there's dead plus earthquake, and then there's dead plus live plus earthquake. But in addition to these, I have an area over here which works through a customizable file where I can actually create any kind of a generic load combination based on my basic load case types. And I've created a generic load combination called 1.4 dead plus 1.6 live plus crane full. That's 1 into crane full basically. So I'm going to add that to my list coming from the AISC AST requirements. So I want it to create all the load combos of the AISC AST requirements in addition to this generic load combo. And when I say generate, it asks me that, are you sure you've created the load cases appropriately? I'm saying yes. And the moment I do that, if I go back into the load combo thing, my load combo area has been populated. And if you see over here, it has created, I don't know how many load combinations, but if you see there is dead plus live, then dead plus wind is 4. There are 4 of those because there were 4 cases of the wind, 4 sub indices. And then dead plus live plus wind also has 4 load combos. Then dead plus earthquake has 4, and dead plus live plus earthquake also has 4. And then there is one, the separate one which I asked for, which combines the dead and the live and the crane full. Since there were 2 crane states, it made 2 load combinations. Like I said, if you had 20 crane states and you wanted to combine them with the wind as well, this could easily run into hundreds or even thousands of load combinations. But the feature is very powerful. All you do is you define your generic load cases, your load combos, and you define your load cases with the appropriate sub indices, whether they are cranes or wind or earthquake or whatever, any load case which can take multiple forms or shapes. You define them and then you just run the combo generator and your load combos will be generated. So here, for instance, is a case with a crane which is running around these 3 bays, and it's got 3 wheels on which we have the loads, and on the other side actually we have the minimum loads on the other side and the maximum loads on this side. And automatically what the program will do, it will create all the load cases for each position of the crane. If you see, the state sub indices are changing, and this has not been entered manually. This is for the load cases, by the way. And even the load cases can be generated automatically for moving loads like cranes. And there are, I mean, it's not like 10, 20, but there are probably, I don't know how many there are. There are about 550 positions, very small increments which the crane can take. And what it will do is create all the load cases, and if you want all the load combinations for you. And then what you can do is you can just simply run through them, and you can see how the load is moving on the screen, and the moment diagrams of the crane girder is also changing according to the position of the loads. And you can use this feature very conveniently for creating multiples of load cases and load combinations in Comosys. And if we were to keep moving, for example, we could see that the maximum loads would switch to the other side and the minimum loads to this side. And now you're creating the actions on the other side of the hall. And obviously the building itself is getting the loads from the crane transferred to the columns and then to the foundations as well. Now coming back to the issue of load combinations, standards sometimes dictate that for instance, they will say that you can have a certain wind load on the building for the whole building, but for the individual girts, it will ask you to take a higher wind load because of gust factors or some other reason. So it will ask you to take a higher load for the individual for the design of the individual girts, but for the entire building it will ask for a lower load. Now, if you put the higher load on the girts, then the entire building design will be affected, and you don't want that. So what typically engineers will do is they will create two copies of the model, and in one copy there will be the lower normal load which will be applied on the building, and in the other copy there will be the higher load, but this time they will only take the design for the girts, for example. Now in Comosys, what we have is we have an option called element specific load combinations. So when you create your load combinations, you can add other load. So for this is the normal load combinations have the wind factor of 1, but I've created an extra one over here in which the wind loads have been amplified by 40%. But for this particular load combo, I'm going to open this flag called element specific. So if you remember the name, it's dead plus live plus 1.4 wind, and I'm calling this one element specific. So when I do that, this combination will not be used for the design of the building. Where will it be used? If I go and select any girt or multiple girts or whatever, and if I double click them and I go to my design 2 tab, over here I will start seeing those element specific combos which I created. And now I can say I want to use this element specific combo for the design of this member. So now this combo will be used only for the design of this individual girt and not for the design of the building, and this will save you from having multiple copies of the same model again and again and then going through them for your design reports and this and that. Now, once we are done with defining the load cases and the load combinations, we would naturally like to proceed to the stage at which we define the loads on the building. And there are many ways to define loads on the buildings, and some of them you can see on the screen right now. You can assign joint loads, you can assign frame loads, and inside the frame loads you have several options for uniform loading, concentrated loading, trapezoidal loading, and temperature loading, and you can select the load cases, etc. over there. You can also define monorail and crane loading, which we kind of saw a bit. And you also have surface loads for shells and this and that. But I want to start off with something which we call the load transfer polygons. And these are extremely powerful polygons which can be used to transfer loads on your floors, on your facades, on your roofs, or basically on any plane. As long as there's a plane available, you can use these load transfer polygons to transfer loads on that plane. So what do these load transfer polygons look like on the screen? So let me turn on their visibility from this section over here where you can turn on the visibilities of all the objects in Comosys. And over here on the right hand side, you have floor polygons and you have your visibility and your selectability options. Every object in Comosys has visibility as well as selectability. So I turn on the visibility and the selectability of the floor polygons. And when I do that, these orange polygons appear on the screen. And these are what we call the load transfer polygons. They can be double clicked. They have their own property editor, which we will talk about. They have multiple, they have properties according to which the load can be transferred in both directions or in one direction. If then according to your need, you can, for example, double click on that and you can change the load distribution to two-way rather than one-way, or you can bring it back to one-way, or you can keep it automatic depending on your needs. But this is what the load transfer polygons look like. And now I will talk about how you actually go about creating them. So here I am on this floor. The level of this floor is 15,900. And I want to create those orange polygons you just saw on this floor. So all I do is I go to this floor menu on the right side, on the left hand side, and I create a floor called 15,900. The name can be anything actually, but I'm just giving it the same name as the view so that I can recall it easily. And it appears over here in the list of the already existing floors. And now all I need to do is I go to my frame load command. I can do it from here, or I can just right click from here as well. They both lead to the same place. But if I go from here and I say, okay, the relative level from this level will be 0. So this is at 15,900. I don't want to give it any offset, so 0 is okay. And then it asks me for which floor from the ones created on the left hand side. And if I go all the way down, I've just created this new floor, 15,900. I say okay, and the moment I do that, these orange polygons are created. It basically goes and finds all the possible combinations where loads could be transferred in this building. So let me turn on the beams like that so you can see it more easily. It finds every possible area where you could have a load transfer, and for that possible area, depending on how the releases of the elements are, it also suggests a load transfer direction, which you can then modify later. You can convert all of them to two-way or all of them to one-way. You can change the direction of which direction you want to apply the loads. But the whole point is that without you having to even select any points, it will create these polygons for you. And then what you can do is you can actually delete some of these polygons. And you can say, okay, I don't want any loading over here. I don't want any loading over here. This is a hole, I know that, in the floor. So you can actually go in and actually modify this list according to whatever your architectural requirements are. Once you have removed the floors, which represent, removed the floor polygons, which represent, which have covered areas which are supposed to be holes in the floor, for instance, you can go ahead and modify the loading, the transfer directions. So, for example, if I wanted to change all these into two-way distributions, I could just select the floors by the on-the-fly filtering, and then go in there and say I want these to be two-way as well, and those would be converted into two-way. You can select the whole floor and do that. Now, once you're happy with that as well, now the time comes to actually apply the loads through these floor polygons. Now, to do that, all you need to do is just go to the floor polygon, which we have created at the 15,900 level, right click and say, I want to create a surface load using these polygons. And you select that option, and this little dialog box appears. You can select a load case. So let's select the live load case, for example. And the direction can be, you can have global X, Y, Z directions, or you can say perpendicular to polygon. So like I said, you can do wind loads on roofs or any inclined surface. So in this case, I'm going to leave it at global Z, and I'm going to give it a name. I'm going to say live load, and then I'm going to give it a value according to these units. So let's give it a value of -5 kilonewtons per square meter for these floor polygons, and say OK. And when it says, do you want to create the surface loads? Yes. And the moment I do that, if I open this up, this little live load has been created on that floor. Now, if I were to then sort of rotate this around and look at it like that, and turn on my live loads from over here, the reason why they didn't show up is because the visibility of the loads is off. So if I turn on the visibility as well, you will see that all the live loads have been created from those floor polygons. And in what amount? What is the quantity? That quantity depends on what you just did in there, whatever number you just gave. You can go in and change that number now if you want. I just wanted to show you how easy it is for a very complicated floor like that to create your loads. And even now, after you've created your loads, you can still go in and, for example, delete certain polygons. And when you do that, the floor loads will be modified accordingly immediately as you delete the polygons. So let's say somebody tells me that even this part doesn't have a flooring on top of it. When I do that, you see that the loads are being modified as we delete those polygons. So this is a very easy way to create your floor loads. Here is an even more complicated case of, you can see the building on the left, and on the right hand side you can see the floor polygons at this level, which is the 8,550 level. And if I were to turn on the loads, you could see that all the floors. We have removed the polygons where there are openings in the floor, and you can see the openings are very complicated in this case, much more complicated than the example I showed you before. But the floor polygons have been used very efficiently to create basically your floor loads. Now, if I were to go in there and select a certain group of these floor polygons and press enter and through the on-the-fly filtering, if I were to double click on the polygons only, I could just ask them to, so right now they're transferring the loads in both directions. If I were to say, okay, instead of the two-way action, you can, I want to give to create a one-way action for these particular floor polygons, and I do that, and then I go to my this floor level and I say just recalculate the loads according to this new definition. When I do that, immediately the floor loads will be recalculated according to the new load transfer direction. Now, if you were doing an earthquake analysis, say based on the equivalent static load method, what you would do is you would find the equivalent static loads at each floor level and apply them as horizontal loads on the, say, the columns directly at certain node points, and that will give you the overall impact of the equivalent static loads on the foundations and on the braces, etc. But we know that in reality, the earthquake loads actually stem from the accelerations of the mass inside the floors. So it's not correct to actually just assign them to the columns directly. Just like it's incorrect to assign wind loads directly to the column, they're actually coming through the girts or the purlins. Similarly, the earthquake loads are also coming through the mass which is available inside the floor, and through the live load through the live load participation, which is once again present inside the floor. So what you can do with these polygons, another thing which you can do with these polygons is you can ask it to create, say, another surface load, but this time you can choose a load case, of course. But instead of choosing the global Z direction, for example, let me choose the global X direction and call it the earthquake X load. Let's say my equivalent static load on this level is 10 tons, and the area of this whole thing is, let's say, 100 square meters. So that's like 0.1 tons per square meter. So I can actually go in there and say something like 0.1 kilonewtons per meter square, say, for example. This is my earthquake load in the X direction using these polygons. And what I will, if I do that, it asks me, do you want to create the load? If you see on the screen, it has actually created horizontal loads using these polygons once again, wherever they are perpendicular to the beams. So let me turn the beams on. Whenever they're perpendicular to the beams, they have been created as lateral loads. And whenever, for this beam, for example, over here, it's being applied as an axial load directly inside the beam. So it'll end up as the same 10 tons which we wanted to give to the columns, and the columns will receive the total of 10 tons, and that will be transferred to the vertical braces and from there to the foundations. But the actual small moments which in real life do occur on these beams as M22 moments, for example, and all the loads in these horizontal bracings, etc., will actually be much more realistic if you apply the loads in this fashion. Now, as I had said, these floor polygons are not really restricted to floors. The name is floor polygons, but they can be used on any plane in space. The plane can be an inclined plane, it can have whatever orientation. So over here, I have created a roof plane. This plane, as you can see on the left-hand side, it's an inclined plane. And on this roof plane, I've created a view. And using this view, I'm going to just ask the program to create the polygons for me. And I'm going to give it a level of 0 because the relative distance from that view is 0. I'm just going to say OK. And immediately you see these floor polygons are now created on the roof plane. And I have filtered out the sag rods and the horizontal bracings from this view because I don't want the polygons to be broken at those levels or at the roof bracing levels. And because I've done that, now these floor polygons conveniently are located between the purlins, and they will distribute the load left and right of the purlin. And now that I have the polygons, I can once again conveniently take them and I can right click and say create surface loads. I can say, for example, I want to create a snow load. I'll say perpendicular to polygon this time because the polygons are inclined, and I want to create a load which is, let's say, the roof wind load. I shouldn't say snow load, but snow load is vertical. But let's just put it in snow load for the moment. Let's give it a name, roof snow, and assuming that it's actually in the direction of the wind. But I'm going to give it a value of 1 kilonewton per meter squared. And the important thing is it's perpendicular to the polygons, and that's what I wanted to show. So when I say OK and it's created, the snow load option is open. And as you can see, the roof loads have been created perpendicular to the polygons, as you can see over there. And if you can also notice, the last purlin got lesser load because the tributary area was less from the left, and the other ones got the same load. So these floor polygons are extremely convenient to create all sorts of load. You can use them to create wind loads, snow loads, live loads, earthquake loads in the X and Y directions. Basically anything which resides on a plane, you can use these polygons to create. Now, without wasting too much of your time, I want to move on. So I'll just show you that there are obviously, you can assign joint loads. You can select any joint and give it a joint load in the form of forces or moments. You can assign joints, displacements as well. We'll talk about them later. You can assign frame loads. So if you were to select any particular frame and you went into the frame load command, you can actually assign uniform loads or concentrated loads or trapezoidal loads or temperature loads, and you can, for each one, you will have different parameters to enter in the dialog box. And you also have these other ones which we talked about. I won't be talking about the area loads which are applicable on shells, or area loads or line loads or point loads on shells. We'll get to them when we talk about shells. But the whole all kinds of manual loading is possible, and you just need to know that at the moment. So I just want to move on to the to the next topic. Now let's move on to joints and what we can do with them. So we had discussed these yellow and blue joints before. The yellow ones were end nodes and the blue ones were intermediate nodes. What you can do with them is you can select any one of them, double click on it, and it will give you this option of adding a restraint to that particular joint. And you can obviously have U1, U2, U3, R1, R2, R3. Those are the restraints you can have. If you press this one, then the whole thing gets fixed. Press this one, it's a hinge. This can be a roller. You can modify them manually as well. But what else can you do with joints? You can select any joint and you go over here and you can assign a joint mass to that joint. And the joint mass, you can give it a name. You can give it translational masses in the 1, 2, and 3 directions. And you can give it a mass moment of inertia about the node in the local axis 1, 2, 3. And you can define the units over here. That's one thing you can do with joints. Another thing you can do is you can assign joint springs. So if you want to model the soil and you don't want to make it fixed, but you want to model it like a spring, then you can assign a joint spring. Similarly, you can assign joint restraint, which is what we just talked about. And you can also assign multi-joint constraints. Now, what we mean by that is if you select more than, let's go to the site, for example, if I were to select an entire floor and select the joints on that floor, and if I went into the assign multi-joint constraints, I have the option of assigning, making it a rigid diaphragm, or giving all the selected joints an equal constraint, or giving the selected joints a rigid body constraint. In the case of a diaphragm, you can give that diaphragm a name. You can define the constraining axis, which is usually Z for the horizontal floors, but you can even make it along any plane. By selecting the auto option, whatever plane is defined by those joints, it will be taken to be perpendicular to that plane. With the equal constraint, then you have the option of defining which particular degrees of freedom will be equated as far as those joints are concerned. You can give it a name once again. You can save them away. And for the rigid body one, you only need to give a name. There's nothing you need to define because the bodies the selected joints will behave like a rigid body. There's a difference obviously between a rigid body constraint and a rigid diaphragm. The rigid diaphragm doesn't behave like a rigid body. It behaves like a rigid body only inside the plane, not outside the plane. Now, since we talked about assigning masses to joints, let me just remind you that you don't always have to do that. When we go back to the load cases, and in the load cases, you can specify any particular loads in a load case to be converted to mass during the analysis stage if you're doing a dynamic analysis. And you can say that any load which I enter under this load case, you convert it to mass with a mass conversion ratio of whatever this number will be not, codes will usually specify these numbers, and 0.3 is a very typical number for live loads. And the reason they have that is because the live loads are usually modeled as frame loads, but in reality they exist as masses as well. But the participation is not 100% because of various reasons. And what the code specifies is that you should actually consider the mass when you're solving for the dynamic properties of the structure. You should consider the masses of these live loads or equipment loads or basically anything, any load which is there physically as well. So you have the option of converting these live loads or other loads into masses from the load cases as well. So when will you actually assign a mass to a joint directly is when you will not have the equivalent load for that, or you haven't converted that load into a mass. Now, what it will do is if you tell the program to convert it into mass, if it's a joint load, it will be directly applied as a mass to that joint. But if it's a frame load, then the load on that frame will be divided into two parts, and one part will be assigned as a mass to the left node, and the other half will be assigned to the right node. Now we've talked about entering the basic frames and how to give the joints restraints and constraints, and then how to create load cases and load combinations and all that. And it seems that we are now ready to run the model. But there's one thing we haven't talked about, and we need to talk about that first, and that is shells. Now we know that no analysis model is really complete without shells. Maybe not that much in steel, but especially with concrete structures, we have to model a lot of times our shear walls and our slabs, etc., using shells. And so I need to tell you about the various features we have in Comosys regarding shells. Now, the first thing which I need to tell you is that in Comosys, you don't enter shells directly, but what you do enter is something we call supershells. And supershell is based, so I'm going to enter a supershell. And what you do is you simply go around the entire floor, for example. So let's let this be the entire floor. And the supershell appears in front of you. Now, if you double click on that, you open the dialog box of the supershell. And here you can change how it will be drawn. So I like the contoured solid. There's the thickness of the supershell, 200 millimeters at the moment. There is a uniform density of because the supershell is going to be meshed for the analysis. So right now it's about 1 meter. And there's a default material which we have, and we can change that to any other material. For example, I can go down and I can convert it into, say, a C35 concrete. 200 millimeter thickness, and say apply. Okay, and now we have entered the properties of this supershell. If we were interested in how this is going to be meshed, then all we need to do is just press this button. This is like a default preview, a preview of how the mesh is going to come out. And if we do that, you will see that this is what the mesh is going to look like. One thing I want to say at this point is that these beams you see over here, because the supershell will be meshed like this at these points, for the finite stiffness matrix assembly, this beam will also be broken into little parts in the background. You won't notice that, but in the background, while it's assembling the stiffness matrix, in order to have a continuity in the displacements, these beams, wherever they're touching the supershells, they will be broken down into their own subparts. Now, these supershells have some really amazing features which really make your life easy when it comes to the analysis of shells. And one of them is its ability to sniff out or locate whenever there's a frame element touching it. So I already talked about how these will be meshed because the supershell is in contact with it. But this is not only at the edges. If I were to, for example, enter a beam like that and say DX 1000 using the static entry method, and at the other edge, if I were to say DX minus 1000 and basically enter the inclined beam like that, and now if I ask the program to give me a preview of the mesh, you will see that now the mesh has changed and it's going along this line of the beam. And this, not only will this beam be broken down into subparts, but the mesh created by the supershell is also in perfect union in perfect harmony with that particular frame element. But that's not all. Let's say we were not happy with this density of 1000 which we see on the screen. let's say we wanted a higher density, but the problem was that, so for example, we could just make the density higher. We can call it, say, 300. And when we do that and do the mesh again, we can see that the density has been changed, and once again it also fits the beam along that line as well. But this is not what we want to do. What we want is to keep that density of 1000. Let's keep it back to the normal number. And but we know that for some reason there's a stress concentration in this area, and we want to have a higher density, but only around this point and not on the entire slab. So what we do is we go to our mesh modifiers and we say I want an internal point at this point. That's the first thing we do. And the next thing we do is we want an internal mesh density at that point. And we put that element over there as well. And then we can just select them and press enter. And for the density point, what we can do is we can say we want a density of say 250 at that point. And if this number is whatever this number is, this number should be about 3 times that number. So let's call it 750. This is the radius around which it will spread out. And once I do that, and then I press this preview mesh again, you will see that the density has been reduced around that point only, and it slowly grows back into this normal number of 1000, which we had elsewhere in the supershell. But it's not just internal points which we can have to modify the density of the broader region. We can also have internal lines. So I could go to the mesh modifiers and say I want a mesh internal line between, say, this point and this point. And then I can say I also want to change the density along that line. So I can once again select the same 2 points. And once I do that, then I can select those objects like that, go to my density line object, double click on that, and give it a density of, say, once again 350 millimeters, and give this one a higher number because this is a line now, not a point. And once we do that and we do the preview mesh again, we see that not only do we have this increasing mesh size around the point which meets up with this 1000 general density, but we also have the same phenomena going on around this line, and it's meeting up with the broader density of the flag of the slab as it goes out into the outer regions. But even that is not all. Slabs and walls, you know, they can have holes in them, right? And what if this supershell had a hole in it? How would the meshing algorithm behave according to that? So you can go to your cut commands, for example. So what you can do is you can go to your polygon cut, select this supershell, and say I want to cut this. I want to make a rectangular opening in there, and you just select the points, and the rectangular opening is created. And the moment that happens, your mesh basically regenerates. And if we were to select that cut and move it around, so let's right click and say move linear and give it, let's say, okay, any number in the Y direction, and say move, you can see that the mesh is adapting as the cut is moving, even as it is going through that density line. It's very convenient. Let me just remove the cut, and you can see even the density is still being applied along that line, and the cut is being made. And basically all our requirements which we wanted a hole in this area, we wanted the line density to increase along this line, but we wanted the general density to be 1000. All those requirements are being satisfied. Now we know that the supershells are intelligent. We've seen that, and they can sniff out these elements which are lying in the plane of the supershell and mesh according to their presence. But what if these frame elements were not in the plane but were actually outside the plane in the direction, let's say, perpendicular to the plane? So let's say we had a column sitting at this point on that slab and another one sitting at this point. Now these are not inside that plane, so let's make a beam on top of it as well. And let's make matters even worse, and let's go to the analysis tab and create a new supershell, which is like a shear wall, or like a wall, let's say. And let's create it like that, and let's double click on it. Let's change the color just for convenience, and make the settings, turn it into a concrete element, and let's give it let's say a different density of 350. Now we have a different, even more complicated situation in which we've got some elements coming up vertical or perpendicular to this existing supershell, and one of them is a supershell itself, and they're also frame elements like you see on the screen. What will it and the density of this particular supershell is 350, while the overall density of this one is 1000. So what's going to happen at these points of contact? So let's go and ask the program to do the preview mesh for us. And when we do that, we see that this one has been meshed with 350. And as it touches this one is, because the density is higher, it's being forced to adapt to that one. And on the back side as well, you see a perfect harmony between the meshes. And if we were to convert this into line mode, you will see that the columns are landing at a point which is an exact node point for the supershells. So what we have is exactly what we would have done by hand. This would have taken us hours to do. And you can probably already feel the kind of things, the kind of advantages this supershell meshing is going to give you. Those who are thinking about steel might already be thinking how they can use these features to design or analyze steel connections, if you will, to a certain extent. And especially for concrete structures, you've already seen the kind of power it can give. If we wanted to make a shear wall over here, we could just enter a supershell again. Once again, as you know, we don't enter shells, we enter supershells in Comosys, and Comosys does the rest. So we can enter a supershell, change the settings if you want to, whatever. And then if you wanted this bottom part to be restrained, we could assign the line support, for example, and we could just say from here to here there is a restraint. And what that will do, what that will tell Comosys is, if you double click on that, once again, just like the joint restraints, we can have UX, UY, UZ, RX, RY, RZ, constrained or unconstrained. You can remove those. But what it will tell Comosys is that when you're doing the analysis, this is going to be meshed, obviously, this wall. And so some of those joints will come along this line, on this line. So whatever joint ends up on this line, that needs to be fixed like this, according to these fixities. Similarly, just like the line support, you could have point supports as well. So instead of having the entire line fixed, you could have just a point over here fixed, and then whatever node would come to that point would be fixed by Comosys. Now, sometimes slabs don't have a uniform thickness across the floor. So you could have one thickness, and then you could have a slightly bigger thickness in a particular region, for example. So what you do in Comosys is you go to your shell tools and you have a supershell region modifiers. And once you select that, you can select the supershell, right click, and then select the points where you want a different thickness property, for example, or some other stiffness property can also be modified. And once you do that, what it does is, if I were to just say hide this, for example, what it has done is it has created a hole in the original shell, but it has added another shell exactly at that point. And this particular shell now you can modify with a different thickness if you wish. If you just double clicked on that, you can have a lot of thickness. You can change the thickness from there. You can assign it some soil springs. So maybe only this particular part can have some different soil spring, maybe, or some load case related. You can take existing loads from the parent supershell. So a lot of things can be done with these region modifiers, which are very useful. Now, obviously, you can assign loads to these supershells, and if you go to the surface load menu, you can assign the supershell a surface load, which needs to be a uniform load, basically, along the entire supershell. You can also assign a line load, as you can see over here. You can assign a point load, as you see over here. So whenever the mesh will be created, if there will be a node at that point, and the force will be transferred to that node. For the line loads, which you create, for example, when the mesh will be created, there will be an internal line along that. So there will be nodes along this line, and whatever nodes are along this line, they will be these loads will be transferred to those nodes. But more importantly, because these three are common, they're found in most programs. But much more importantly is this loading fields concept, which we have developed in Comosys. And this is really interesting. So let me show you that for a second. Now, most programs have this concept which they call joint patterns. And this is a very difficult concept to utilize, and it's very cumbersome in the real world because your mesh keeps changing. And if you define your joints beforehand and you define the joint pattern beforehand, but then you find out that the mesh wasn't enough or you needed a hole somewhere, then everything needs to be redone. Now, instead of doing that, what we have is these vector fields in Comosys, which you can define. So you can have a linear vector field, and what that means is that you have a linear function in the form, it's a vector function in the form of ax plus by plus cz plus d. This is the function, and you can define these a, b, c, d parameters, and you can set the origin of the coordinate system according to which this function will be defined. And or you can have, instead of a linear one, you can have a quadratic distribution, which will be of the form of ax squared plus a1x squared plus a2x plus b1y squared plus b2y plus c1z squared, and basically that quadratic formation. And once again, you can set your parameters according to that. Or you could have an exponential distribution with a different format, or you could have an exponential type 2, which is a slightly different form of the same function. You can have a power function of type 1 and 2. So you have 6 different types of fields which you can have. And then you can also tell the program that although this field can have both negative and positive values, but I want to only use the positive, I only want to use this where the values are positive or 0, or only where the values are negative and 0. And then, since it's a vector field, wherever it runs into the coordinates run into the actual supershell. So this is the supershell at the back, and this orange is the vector field. Wherever it will hit, so whatever the coordinates of the supershell will be, this vector field will have a value because it's a vector field defined at all xyz coordinates. So whatever the xyz coordinates of your supershell are, the vector field will assign a force at that point according to its own value at that point. And this is extremely powerful, so it can be used in silos for the internal loading of the materials, which are usually not linear functions. There are different kinds of functions are used. And because you have the polynomial option as well, and you have the exponential and the power function option, you can do a lot with this kind of loading. And this is really unique to Comosys, and it will help you solve a lot of your loading problems. Here I've created this little 5-story building, concrete building. It's got 5 floors. I've put one supershell on each floor. It basically encompasses the entire floor, one on each floor, like I said. Then I've got these shear walls, one on the left and one on the right. And the thicknesses of the shear wall is about 20 centimeters, and the thicknesses of the slabs are also 20 centimeters. I think that's the unit, yes. And I have loaded it basically to give a uniform vertical load on each of the supershells in the live load case. It's about, I don't know, about 200 kilograms per meter square or something like that. And then I've given it some wind X loads and some wind Y loads. And basically, I haven't gone into the detail. I've just put some loads at the top level and some loads from in the X direction at the top level and the Y direction at the top level. And those are in my wind X and wind Y load cases. And now what I will do is I will run this analysis in front of you. So what it will do is it will create the mesh at runtime. Like we discussed, we could have had holes, we could have had line loads, all sorts of things would have been possible. But I just want to show you the results of how we check the results of the supershells. So let's run the analysis in front of you. It says the project is going to be saved. Do you want to continue? I say yes. And now it's meshing the entire structure, and it's a fine mesh. So it takes a few seconds, and then it basically finishes the job. So let's check the deformed shape first. That's what an engineer should do first, just in case there's anything wrong with the model. That'll be the first place which makes that apparent. So if you press that button, we come to this different page, and where we have these options to play around with the deformed shape, and we can rotate the view over here like that as well. And what we see is the live load case. Like I said, we had entered the live load case in which there were vertical loads, wind X and wind Y. So right now we're seeing the live load case, and we can, like I said, turn it around to see from various angles. If we press this animate button over here and say start the animation, we can see how it's going to deform.
And while it's deforming, while it's animating, we can also turn it around. One thing I can do is I can change the load case to wind X. And when I do that, I can turn it to the side as well, and I can see how it is deforming. Once again, I can turn it to wind Y, and this time it's the other direction. And like this, I can easily inspect what's happening with the deformed shape. Now let's get back to the structure itself. And over here, you have this contouring option. And if I press this button from here, this submenu appears. And if I go in there, I can set the settings for how the contours will be plotted. So let me do that. So over here, I have the option of plotting either forces and moments on the supershells or stresses on the supershells, or we also have soil pressures and surface displacements, surface loads, and even areas of steel. So I'm going to start off with the forces and moments. And once if you choose the forces and moments, then you have F11, F22, F12. These, as you know, are the shell internal forces. F max, F min, M1, M2. Let's keep it at M1 because we're going to look at the slabs right now. And over here we can have a customized range for the output as far as the M11 values are concerned. We can choose to create contour lines or draw the mesh, etc. Let's just leave it like that. And after doing the settings, we just basically press this button over there, and it's going to create the contours of the results of M11. And on the right hand side, you see this legend, which tells you what are the minimum ranges of the stresses in whatever units you have over here, and what are the maximum you see on the screen. And this is a very easy way to inspect the results. Now, if we were to choose the wind Y direction, for example, to see the results, and go inside and set it to F22 instead of M11, because we want to now see the internal forces in the shear walls. And this is the wind Y direction. So if I turn on the contouring, we will see that we can see how because of the lateral loads in this direction, the shear wall is getting compressed maximum at the ends, of course, and as it's getting higher and higher as you go towards the bottom story. The same can be seen on the other side, and it's very easy to inspect the results like this. Now, coming back to these results for the vertical loads, these M11 results, what we can also do is we can create what we call strip moment lines. So what I do is I just select this button, and I select 2 points. I can select any 2 points as long as they make a line. And then I can select that line, press enter, double click on that, and I can say show the diagram. And when I do that, immediately the moment diagram along that line is created. So if I were to just say, select this one and say show only, if I were to, for example, select this and say show only this one, I can see the moment diagram across that line, and I can place my steel accordingly if reading from the supershells is a bit more difficult. And similarly, I can create this line in the other direction as well. So I can have this line from this direction, from this point to say this point. And now, once again, I can select that line, press enter, double click on the force moment, tell it to show the diagram. And once that happens, I can now see the diagram in the other direction as well. So these strip moment lines can be, like I said, they're lines, they can be in any direction. They're particularly useful if you're doing something round, for example, a circular slab, and you want to place the reinforcement in the radial direction, for instance. But the supershells have been created in whatever coordinate systems which you needed for creating that circular slab. But you want to see the moments along the radial line. So you just basically use this strip moment to create along the radial direction, and you will get to see something like this to see what the moments are along that line. Now, as I had mentioned earlier as well, that if you go to the settings over here, you have these various options of checking stresses or forces or soil pressures, and you also have this option of checking the area of steel. And if you select that, then you have these options of checking the top surface area in the 1-1 direction, bottom surface area required, the area of steel required on the bottom surface. Similarly, along the 2-2 direction for the top surface and the bottom surface. So let's just check for the top surface what our requirements are. So how much area of steel we need for the top surface. And when we do that and we press this button, we see that for the top surface, we basically don't require, so there's 0 over here. This is centimeters squared of area per 100 centimeters. So we basically don't require anything in the middle. We only require the top surface area in this region. And we can check how many centimeters squared are required using the legend over there. Similarly, if we were to go back in and check for the bottom surface, we will get the opposite result, or some because then we don't need any bars in this area for the bottom surface, but we basically need it for the bottom. And over here also, if we know how much minimum reinforcement we're going to provide anyways for the slab, so let's say we're going to provide a certain minimum reinforcement and we know what that number is, so we can put that number over here. And so what it will do is it'll only tell you about the areas where even that minimum is not enough. So if I change the minimum over here in the customized range session, what it will tell us is that your minimum is basically okay everywhere as far as the bottom reinforcement is concerned, but these areas require reinforcement. This is from the range from the minimum to the maximum. The blue areas basically won't require any because you already have the minimum over there. So it's a nice way of checking wherever you want to put some extra reinforcement.
And if it is not concrete slabs which you're designing and you're interested in steel plates and their stresses, then in that case you will obviously go to the stresses section and probably be more interested in the von Mises stresses, and you can easily then tell which areas of your structure are being pushed to the limits, and then you can increase the thicknesses of the plates in those areas. Now there's one very handy little feature which I just want to talk about for a few seconds and then move on. And that is, if you go to your Supershell tools menu, you have the option of splitting supershells and converting plates to supershells. But there's also this option of converting any surface into a supershell. And this is pretty handy, and at times it can really help you quicken your modeling time. So what you do is you basically just select this, and then you can select any surface on the screen. So let me just select this I-beam flange and this I-beam web and this the back of the flange again, and then this web and this flange and this bottom flange, and for the column as well, this one and this one, and for this plate and for the plate at the back. I'm just doing random selection right now, just to give, and maybe I want to select this plate over here as well, and I right click and I interrupt. And if I go into my visibility settings and I just open my supershells right now, you can see that supershells have been created for that area, and I could have continued clicking. And then obviously you have to now go in and do the rest of the modeling. But this will, if you wanted to, for example, somehow model this connection, or it could have been some other instance where you could have used the surfaces to create your supershells. Now each of this is a supershell. You can go in, you can change the density, you can change the thickness, you can use all the features which you talked about for internal lines and internal points, and you can have your points of the bolts, for example. You can have little elements connecting them and stuff like that. But this is just something I wanted to mention, because it is very useful in quickly creating supershell models from something existing which you have on the screen. Now let's talk about viewing the analysis results on the screen. So we can do that in both tabular as well as graphical form. So if I were to select a column, for example, and go over here and say I want to see the joint, the element analysis output tables, we can select any load case which we want from here, and for that column it will tell us about all, because this column is a huge column. It's going from this story all the way 2 stories up, and these stories are pretty tall. So it'll give it from the start segment 1, segment 2, segment 3, all the way down till the end of the section. And you can even ask it to increase the number of points for each segment, and you will see all your 6 major results: your axial force, your shears in the 2 directions, your torsional moments, your moments M22 and M33, etc. If you want, while the table is open, you can switch to another element
If you want, you can select multiple elements, and the entire tables for all those elements will be presented to you in tabular form. What you can also do is to select any element, and then instead of the tabular format, you can do it as an internal force diagram as well. So once again, I've selected the same column and I've chosen the live load case, and I can move my mouse cursor over the column, and I can see the actual values in whatever units which I want. And I can see values for the axial force, the torsional moment, the bending moments, etc., and even the deflections, depending on what load case I choose. If I wanted to see the results for the entire building in one go and not element by element, I could just go to this command over here and say turn on my M33 moments for the entire building. And then I can zoom in and see what their relative values are. If I select a particular element, then the values of that particular element will be shown. If I just don't select anything, then everything will be shown, but that obviously becomes a clutter depending on how complicated your building is. But what you can do is you can go and select any particular element, and then you will see the values of whatever moment diagram or shear force diagram which you are printing on the screen. Now, let's say we are in this view, which is a plan view, and I wanted to look at the M33 moments, for example, for the elements which are visible in this view. If I press that, I'm not going to see much because the M33 moments are out of this plane. So what I have the option to do over here is to say project to the current view. Now, if I do that, then my M33 moments are projected to this view, even though they're actually in the other direction. But since I'm working in the plan view, this provides a handy tool for me to see which particular beams are being stressed the most and where the moments are the maximum and stuff like that. So this ability to project to the current view is very useful when you're working in plan or sectional views. Now I want to move on to the design capabilities of Comosys, and I want to start off with the basic tab, the basic design tab, which is in the dialog box of all frame elements. If you double click on any element, we see this dialog box, and I want to quickly go over the basic parameters which are available over here so that basic understanding is achieved. So the first thing we see over here is check for lateral buckling. And this tells the program whether we want this particular element to be checked for lateral buckling. We can turn it on or off, depending on whether we want that or not. Now, this is an interesting flag over here, which means provides buckling support. So what this tells the program is whether this chosen element actually becomes a supporting member for other elements. So for example, if I were to choose this particular beam and double click it, and I say that this one does not provide buckling support, then the buckling lengths will be calculated as if this element does not exist. And these ones exist, but this one does not for the beam, for example. But if I were to open that back up, what that will tell the program is that this particular element will support the elements it's connecting to. So it's connecting to this beam and to that beam on the two sides. And therefore, it will provide buckling support for them. Now, this obviously depends on, maybe this is not a good example, but if we had, for example, girts over here or roof purlins, you might or might not want to include them as providers of buckling support for the column. In industrial buildings, it's very common for the girts to be removed temporarily for maintenance purposes and this and that. So although they do exist, but you might not want to consider them for your buckling support. Now, continuing with the tab, there's this thing called forced. What that tells the program is that you don't want this element to be designed by Comosys. You want to force this particular section. You don't want any optimization. Maybe there's an architectural requirement, maybe there's some other requirement, and you don't want to basically allow the automatic algorithms which work for design to act on this element. You can tell whether it's a rolled section or not, and that obviously can change the design. This is important. So for example, in columns, the columns might be braced in this direction, the main direction, or in the web direction, or they might not. And depending on whether they are braced or not, whether the structure is braced or not, you will turn on these checks. Here you have something called the design restriction, which I'll talk about in a second. More importantly, over here you have your design sections, which I'll talk about when I'm explaining the design procedure. This is the number of design points for each segment. So every element will be divided into segments. So even this beam, for example, it's a physical beam going from here to here, but it has lots of things connecting into it. So it's composed of many sections. And so we have section 1 over here, 2, 3, 4, 5. So what that number is telling the program is that each section will be further divided into 4 points, 4 design stations to do your design checks. There's something about a cantilever deflection check, which I'll talk about, and there's the ability to override your buckling lengths as well. So let me just close that and we can continue with explaining what the design parameters. So now let's start with the buckling length calculations of elements, as that is really a very problematic area in most programs. And a lot of, if you actually input your structure according to the detailing requirements, then the programs really mess up when they have to calculate the buckling lengths. So what I've done is over here, I've divided this beam, this physical beam into 3 parts because I want splices over here in the detailed model. But as far as the buckling length, I know, as far as the main direction, the entire length of the buckling of the beam should be used for buckling in the strong direction, and in the weak direction, obviously these ones will restrain the beam from buckling in the weak direction. So I want them to be considered as well. So we have over here, if you go to the analysis and design menu, we have something called the unbraced length. And this can be checked for both the 2 direction and the 3 direction, 2 being this axis and 3 being that axis. So if I were to press the unbraced length button and then hover over this beam, I'm expecting the entire length of the beam to be shown as unbraced. And for this side, I want these elements to basically restrain it. So let me go over press this button and go over this beam. And as you can see, if I'm hovering over that beam, despite the fact that it's limited, I've broken it, it's still showing the entire length of the beam as my unbraced length in the stronger direction. If I were to press the 3 button, which basically tells the program to now switch to the other side, it shows you can tell the green, the red, the green, the red. Those are alternating segments for the weak direction, and it's telling me that in the other direction there are restraining elements, and we've got 4 segments, and in each segment the buckling length will be the lengths of those green and green and red alternating segments. If I were to, for example, interrupt and come over this middle member and do the same thing again, once again you will see that when I hover over the middle member, that also is shown to be the entire length is shown in the stronger direction. And if I press 3, then we get these intermediate areas for the buckling lengths in the other direction because of the existence of these. Now we talked about this this feature called let's go back to the design tab, and as we said, provides buckling support. So if I were to remove that for, let's say, this particular element, and this one now does not provide buckling support, and if I were to go to my unbraced length again, so this is the strong direction, and let's press 3 to see the weak direction, and you see that in the weak direction it has now skipped that element. It's telling me that there's a red portion in the beginning, then there's a larger green portion, and then there's the final red portion for that element. And this larger green portion has basically skipped over the element which was coming perpendicular to it, which would normally have supported it, but since we've turned it off, it's no longer supported. Now, another thing which I can do is, instead of doing this, I can leave this on. I can say it provides buckling support, but I go in and give it an axial release. Now, in this case, once again, if this element has an axial release, whether on the start or at the end, it doesn't really matter. It's not going to provide buckling support in the weak direction. So although I have that particular feature on, the one in the design tab, that it does provide buckling support, but my analysis constraints are different. And now, once again, if I were to go to my unbraced length command and go over this, for the stronger direction, we have the whole thing. And for the weak direction, once again, we see that the element has been omitted. Now let's talk about a column, for example. So let's select this column, and this column is going across 2 stories, but it's also extending into this third story a bit. But with the point where it is ending, there is nothing to restrain it. It's just continuing to connect with the column over here. So if I were to do, if the program was to do, if there were any design sections over here in this region, the buckling length which needs to be taken for those is not just this little stub which is coming out, but it should be the entire segment all the way to this point until you get to these lateral supports for the other column. So if I were doing any design checks over here, my segment length should be this whole length all the way all the way to these constraining restraining elements. Now if I were to go to my unbraced length command and select this column, you can see that in the bottom area which I just showed, the entire area has been painted red. That will be the segment length taken, although the column actually stops short of that. So this feature is extremely powerful, and what it allows you to do is to focus on your detailing as well. You can check your splice locations. You can model your columns and your beams according to the actual splices where you want them, and you can rest assured that you won't need to override the K factors and the buckling lengths and this and that, because they're really time consuming. And every time you run the analysis and you have and the section changes, if you have to go back and modify those factors, then that's really a big problem. In Comosys, the buckling lengths and the unbraced lengths are calculated very accurately, even if the element is composed of several parts, even if it falls into a segment where the element after that needs to be considered, as you just saw on the screen. And this is a really time-saving feature. And the same intelligence is available to you for the deflection checks as well. So it's not just the buckling checks. So for example, if Comosys was to check for the deflection of this element, it will know that even though I'm checking along the stations over here for this little stub, I will need to take this entire length into consideration. So let's say the deflection limits are L over 500. Then which L do we use if you're doing the design of this element? Do we take this L, or do we take this and this put together, or do we take it all the way? So once again, the same intelligence which we just saw for the buckling lengths is also available for the deflection check. Now you do have the option of actually going to your design tab and actually overriding the variables, the automatically found unbraced lengths around the 2 direction for each segment. So this if you want to override, for example, you could have several numbers entered. So you could say that for the first segment, the unbraced length is 3 meters, and for the second segment, it's 4.5 meters. For the third segment and onwards, it is 5.5 meters. So you can override just in case you want to do something different, but in most cases you will not need to override, and that will be a huge advantage for you. And you can do the same for the effective length factors K22, K33. But once again, if your releases have been entered correctly and your buckling lengths are correct as well, then your K22 and K33 factors will also be calculated correctly. But you do have this option of overriding the result. Now, I want to talk about a concept which I feel is extremely important as far as the design process is concerned. And this is something we call design restrictions. Now, as you know, in most programs, when you want to get something designed, what you typically say is that you use sections of that particular family, for example. So let's say IPE family, and the program will go through all the members of the IPE family and find one solution for you in that design loop. Now in Comosys, we've gone a few steps beyond that, and we've created this concept of design restrictions. And what design restrictions, you can create as many as you want, and then you can assign those to any element which you want. But what does a design restriction look like? So let me open up this existing design restriction. And what this is saying, you can give it a name. So I can call this beam or column or vertical bracing of bottom floor or beams up till the second floor. As many names as you want, as many design restrictions as you want. But in each of them, you can put multiple families to begin with. So you can say that I want you to try the HEA family. And then if it doesn't work, go to the HEB family. And if that doesn't work, go to the YP family. If that doesn't work, try this one. And if that doesn't work, try this one. And for each one of those, I can have further limitations. I can say that when you're trying the HEA family, you should only use those with a height of greater than 300 millimeters, for example. And since I'm designing particular beams, I want the flange width to be greater than or equal to 150 millimeters. So while you're going through the entire family, make sure you're sorting out these constraints. And you can also go into the manual selection and say that, okay, when you're doing the HEA family, don't check for all the available HEAs, but check for these ones and these ones and these ones, and don't check for the rest. Well, this is a very powerful feature. And you can also tell it to limit your lambda. For example, if this is not for beams, but say for vertical braces or horizontal braces or columns, you can limit the lambda if you want, the buckling length related lambda values. And you can, but one other thing you can do is, for example, if you're doing it for vertical bracing, you can create a design restriction. Let's create another one, for example, and call it VB. And you can say that when you're designing the vertical bracing, I want you to try single angles. So you double click on that, but then you want to try your twin profiles as well. So for that, what you do is you go to your twin section over here and you say, I want you to try back-to-back angles after checking single angles. And if that doesn't work, I want you to try cross angles. And if that doesn't work, I want you to try back-to-back channels. And if that doesn't work, try face-to-face channels. And if that doesn't work, I want you to come back and do an HEA section for the vertical bracing. So you can have a complicated design restriction set up like this. And for each one of them, you can have limitations on the HPST values. For the cross angles, you can say when you're doing that, put a distance of 12 millimeters between them. For the back-to-back ones, you can say you can have the same distance depending on your detailing requirements, etc. So you can have very complicated scenarios, and you can also have this feature called a use priority. Now, what that means is that it will first go through the angles. It'll then try the back-to-back angles, and then the cross angles, and then the back-to-back ones, and this and that. But if you remove this flag from here, what it will do is it will put all these families, all the angles and the back-to-back angles and the cross angles and the eye profiles into one bag, and it will sort them according to their weights, linear weights, weight per unit length. And then so it could be that it tries an angle, and the next thing it tries is an HEA section, and the next thing it tries is a back-to-back angle. They will be sorted according to their weights. But if you put the priority back on, what that will mean is that it will basically check them one by one. Now, this is useful, for example, if you're doing, for example, if you had a beam. So let me just remove these. Let's say you had a beam type of a case in which you wanted to check for INP as well as HEA. Then you know that if you tell it to go all the way till the end of the INP section and then come to HEA, this might not give you a very good result. The reason being because INP profiles are don't have wide flanges. And if the beam had a little bit of M22 in it, maybe you would find a solution right at the end of the INP series, which would be a very uneconomical solution. So instead of doing that, you remove the priority and you say that you mix them up and whichever one works. So maybe it'll try the smallest INP and then it's going to try for the HEA one, and that might work according to the weight. So these are very powerful features, what we call design restrictions. And what you can do is you can create as many as you want, and then you can select any member, and you can go to the design tab, and inside you can say that this element will be designed according to this design restriction. And you can do that with the multiple selection as well. For example, you can select all the beams over there, and you can say all these will be, or what you can do is you can go like that, and you can say enter. Or let me just turn on the on-the-fly filtering. Say go to profiles, turn according to beam groups, and say only select the beams. And then you can say I want these beams to be designed according to this design restriction. And these are this is a very powerful feature which will really clean up or make your design process very well.
Now, once we are done with the analysis, we can proceed with the design. And we have these options of either checking elements or designing elements. These are two different options. You can check a particular element, which would be check selected, or you can check all, or you can check a particular subset, or you could design the selected elements, or you could design the entire structure. And so let me just, what's the difference between checking and designing is that what checking will do is it will take the existing section. So if this is the existing profile, for example, it has a certain size. And what check means is just use the existing section and do all the design checks at all the stations. Right now, if I were to select this element, the analysis has been done. But if I were to say, show me the design data, it's empty. The element has no design information. It's just been analyzed. But if I were to select it and say check selected, then immediately the program performs a design check on that element. And after having done that, I can go and check the design data. And this time the design data is filled. And you can see over here your final stress results. This number should be less than 1. Basically, the summation of your axial forces plus your bending moment and your bending 3-3, the total should be less than 1. Right now, it is less than 1. And it'll give you the exact locations. It'll say that the most critical combo was this one. At a location of 0, the axial force was this much, the bending moment was this much, etc. Your lambda or your inertia parameters are given over there, your K factors, your unbraced lengths, and your design related variables, and the final analysis. And it will also do over here your shear checks as well as your deflection checks. So it will do the analysis, but this is basically a design check. So it's not really designing the element, it's just checking it with the existing one. Whereas the option of designing it would mean that, okay, you don't change the profile, keep it as it is. Obviously, to change the profile, you would need to unlock the model. But you assume as if the loads will remain the same, whatever the current loads are. But you find me a section which will work for the case. And how will it find this section? It will use the design restrictions which we had provided. So, for example, this particular beam might have some design restrictions. Let's go to the design tab. So it has a design restriction called, it has a name over there. And this particular design restriction is over here. We can go in there and this says check for HEA, check for HEB, YP, IP, and this and that. So if you instead of saying just check all, if you check the selected one, if you say design the selected one, it will go through this design restriction and find the appropriate section for you. So let me just do that. Let me double click on that. Right now we just did a check, but if we were to select this and say actually design the selected one, then what it will do is it will suggest a section for you. It will tell you that this if you use this section, then this will give you the optimum result, and then you can modify the existing section according to that, and there are very quick ways of doing that and replacing the thing for the whole building, etc. And we will obviously talk about those as well in a minute. Now, instead of checking a particular element, let's just go to this check option over here and say check all. And this will tell the program to check all the members of the entire building. So let's just press that. And very quickly, it goes through the design of all the elements and all the stations and all the load combos. And in a few seconds, it's completed. Once the check has been performed, we can turn on the color coding from here. And immediately on the screen, you can see that the elements have been color coded according to their design ratios. And you can set those colors up, of course, in your settings by going over here and defining. You can add to these ranges. You can make them more refined, and you can also limit the color coding according to, because obviously when an element fails, it can fail according to your capacity ratio, or it can fail according to your lambda criteria. It can also fail according to your deflection criteria in the 2 and the 3 directions, or it could fail according to your shear criteria as well. You can choose which criteria to consider when you're doing the color coding, and that's a nice advantage to have. But anyway, coming back to the subject, it color codes on the screen, and you can see that the elements are either green or blue, which is okay, and the red ones are the ones which have a problem. So if we zoom in there and select this one and say, okay, this is failing for some reason, and I want to check the design data. So the axial and bending components seem to be less than 1. That's okay. The shear check is fine, but there's a warning over here for the deflection check. It's not really passing by a big amount. 0.011 is slightly bigger than 0.010. So maybe you can ignore that, or depending on what you want to do. Once again, you can go to other parts of the building. There's another one failing over here. You can go and check the design data. Everything seems to be okay as far as axial is as far as stresses are concerned. Once again, there's a deflection failure. It's like almost double what it should be. 0.04 is greater than 0.02, so you need to do something about this. So this is a very nice and convenient way to check your design results. If I was to say that I'm not really worried about deflections right now, just show me any stress failures for the moment. What I would need to do is I would need to go to my settings, go to my design ratio colors, and say don't show me the color coding according to deflection criteria. And the moment I do that, these elements also turn green, and now only the stress checks and the shear checks are being done. Now let's talk about one-click design. One-click design is a very nice feature we have in Comosys. And to explain that, let's recall that design is basically an iterative procedure. When I say that, what I mean is that you need to you need to load your model, obviously. You need to put the loads in, you need to create the load combinations and this and that. But then you need to run the model, and then you need to check the model, whether some elements are failing or not. And if some elements are failing, then you need to design them to see what section would have made them pass. And then let's say these are whatever 60 odd elements. Let's say when you design them, say 55 of them are actually they need to be changed. So what you would need to do is then go in and change those 55 elements. But the moment you do that, now the analysis results are invalid. So you need to run the program again, run the analysis again. And this time when you do that, now something different will happen because the sections have changed. And maybe not 55, but maybe another 25 elements would need to be changed. And then you would come back and unlock the model, change the elements again, and then run it again. And you need to keep doing this iterative process until you get to a point where basically the elements are not changing anymore. Now, this is what I meant when I said that design is an iterative process. Now, in Comosys, we have something called one-click design. Now, what this does is when you press that, it'll take you through those cycles automatically. What you need to have is these design restrictions, which we just talked about. So I've created 3 design restrictions, one for the beams, one for the columns, and one for everything else, which is basically the horizontal bracings and the vertical bracings. And I've told it that for the beams, your design restriction is you can try the INP section, you can try the HEA section. There's no need to check priority and this and that. So I've got my design restrictions assigned to the elements, beams for the beams, columns for the columns and all that. And for the horizontal bracings and vertical bracing, I've assigned the 3rd one. And now I want to do one-click design. And what it will do is it's going to run the analysis, see whichever elements are failing or over-designed or under-designed, whichever way. They need to be as close to 1, the ratios, as possible. And then it will automatically change all those sections which need to be changed. Run the analysis again, change the sections again, and keep doing that until it converges to a final solution without you having to do anything. All you'll be doing is just watching these things happen on the screen. So let me just go in there and say one-click design. When I do that, it says what is the maximum number of design cycles you want. I can give a large number, but 10 is okay. Basically, I want it to stop after 10 cycles. It could stop after 3 cycles, 4 cycles, but I don't want it to go beyond 10 cycles. So I say okay, and now I want you to please keep your eye on the screen and see that these elements will start changing with every design cycle. I'm going to say okay, and it says project is going to be saved. I want to do yes. So you see the profiles are changing now on the screen, and it keeps going through these design cycles. If I go all the way back, it's finished now. By the way, it's done I think 9 or 10 cycles. So if I go to the first cycle, end of the first cycle, it says that, let's go to the end. It says at the end of the first cycle, 62 profiles were modified of this lot. And the weight of the structure at that point was 3.6, fell to 3.63 tons. Then it did another analysis, design cycle 2. And at the end of that cycle, let's go to the end of that cycle. This time 28 profiles were modified and the weight fell down a little more. Then it continued doing it for another cycle. And this time 21 profiles were modified. And then you keep going on basically all the way till the end until you get to a point where 0 profiles were modified, and this was the final final weight of the structure. It converged to about 3.5 tons for the total structure. So this one-click design is a very nice feature which allows you to use the design restrictions for the elements, and it makes you go and find solutions, optimal solutions. Then you can further refine them, of course, and you might need to do that depending on the particular geometry which you have. You might need to force some elements to be similar to others in this and that. But this procedure basically allows you to very quickly go through the design process through a one-click design button. One very nice and I would say unique feature which we have in Comosys is something what we call the design evaluator. And now in design, normally because of all this color coding and this and that, you can get a design in which everything is green. So you turn on the color coding and everything looks green and blue and yellow and the colors look nice and there's nothing red. And it would seem that, you know, you've got a very nice design. But the reality is that you can get all your colors to be green, and there could be many reasons why the design would not be considered to be a good design by an experienced designer. And there are many reasons for that. Now, when somebody brings me this model after having worked on it for a month and gives it to me and wants my opinion, if I turn on the color coding, I really can't guide them much in 10 minutes. I mean, obviously, if something strikes me as very abnormal in the first minute, then I can. But actually going through every single floor and the way they have set up their horizontal bracing systems and the way they've set up their vertical bracing systems and what maybe things that an experienced engineer would have done differently, but that would require me to actually sit down and work on this model for a day or half a day or some time, and then, you know, come up with my suggestions. So we have developed something called the design evaluator for that. And what you do is you simply select the model and you go to your design evaluator. So imagine this model has been given to me by a young engineer, and I asked for my comments on it. I just press OK, and this fills up this design evaluator form. My whole purpose right now is to spend 10-15 minutes on this model and give the fresh engineer some feedback. So the first thing it does is it gives me a breakdown of all the columns and beams and vertical bracings and horizontal bracings and girts and purlins, how much they are by weight. So the columns are 53% by weight, the beams are 31% by weight, the vertical bracing is 13%, and what these numbers. And I can also see how the columns are generally failing. The normal stress ratio is averaging around 0.57. The lambda ratios are averaging about 0.118, and deflection ratios as well, because we haven't done the deflection checks on the columns. The overall drift check is obviously different. But more than that, although this gives me some idea, but more than that are these two over here. And these are typical areas where fresh engineers will make mistakes. So for example, what I don't want is a lot of my elements failing because of lambda criteria. So my lambda, let's say I don't want my lambda to be greater than, say, 150 or some number. 130, but they have designed it in such a way that a lot of my elements are failing because of lambda. And they would pass if they increased the lambda, decreased the lambda and chose a higher section, the element would pass. But that's not something what I want. What I want ideally is for all of my sections to be approaching 1 as far as the normal stress ratio is concerned. Because that represents optimal use of material. I don't want to have my elements failing because of lambda or deflection. Now, sometimes they have to, but that's not something I want. So this one quickly shows me that I've got 4.12% of my elements which are failing because of lambda critical frames. And what I can do is I can say fill, and because I don't know which one these are, and this list is populated, and then I can select anyone and say go to, and it'll take me to the model and show me exactly what's happening over there. The other thing I don't want over here is deflection critical frames. It says about 3% of your elements, which is fine, and this is not a bad design. I'm just giving an example that 3% of my elements are failing because of deflection. If I press fill over there, this list is populated again, and I can then press go to and go to those individually and see why is there something I could have done differently. Maybe I could have framed them differently and get a better design. Similarly, what I don't want is shear critical elements. I want my elements to fail because of normal stress or bending stresses, not because of shear stresses, typically. So this number is reasonable again, only 1% is failing because of shear, or if shear is governing, I should say, not failing. And 91.744% is the normal stress is governing, and that's a very good sign. So this is a good design. But over here, we see that these are floor beams. And in floor beams, you want basically your floor beams to be dominantly loaded in the M33 direction. So because of their three components, the axial component, the M33 component, and the M22 component, for the floor beams, I want M33 to be dominant. I don't want M22 to be dominant for the floor beams. But this one is telling me that about 8.65% of your total weight of beams has got a very high M22 ratio. So I'm interested in that. Let's press the fill button and go to this one over here and see that, okay, this one has an M22 ratio of 0.449. That's very high. I want this one to dominate. So what I'll do is I'll select this one and say go to, and it takes me to that beam. And if I actually open it up, if I open up the design data, I see that yes, actually the bending 2-2 component is actually dominant. And that's not something I would have liked. So I can then take a look at it more carefully. And it's probably because of these horizontal bracings over there, and they're really pushing into it in a lateral direction. So maybe that will give me an idea about what I can do with that, or what I can suggest, because this is a waste of material. This is not a good way of using this. What the program has done is, because the loads are in the M22 direction, it has optimized this section by just using a bigger and bigger section. But that's not good. I could have chosen a much smaller section had my lateral loads not been there. Or if I had used a different section, maybe a different type of section, maybe. Another thing which I don't want is for my bracings, say my vertical bracings or my horizontal bracings, to be failing or having a significant component of moments in their design. I want them to be primarily working for the axial loads. But you know, sometimes when we have these large bracings, even their self-weight can cause bending moments. And sometimes if they're not supported along their self-weight, that bending moment can take up a lot of their capacity. Now, in this case, we don't have any of those, but there's a limit over here. I think it's, let's see, for axial loads. So it's 0.3. We don't want a limit for ratio of priorities for the direction. So that you can change these numbers over here. So yeah, this is the one, I'm sorry. Upper limit for some of the moment ratios for profiles whose primary intention is to take axial loads. So I can reduce this number to 0.2, for example, and I can see which ones are failing according to that. Then I have this lambda max over lambda minimum limit. This is also important. Obviously, every profile will have a weak direction and a strong direction, and there will be a lambda max and there will be a lambda min. And typically, I would want these two numbers to be close to each other, because if lambda max is much bigger than lambda min, then it's obviously going to fail in the lambda max direction, and that's going to be a waste of material. So this is over here, this is lambda max to lambda min ratio 1.2, which I've specified on the right hand side. And over here, it's showing me all the elements in which the ratio is greater than 1.2. So I can zoom in on those and maybe suggest something to the engineer that don't do it, or put some zero members in that direction or something like that. So these are things which fresh engineers miss. Lambda related criteria, deflection. In the end, they get everything green, and that's okay. But that doesn't really mean the design is good. So you can have lots of elements failing due to deflection. You can have lots of elements failing due to shear. You can have lots of floor beams in which M22 is dominant. You can have bracings failing because of moments. If I were to just take a look at the color coding, I would think, okay, this is a reasonably good design. But my whole idea is to spend 10 minutes, 15 minutes, and give the person some sort of feedback which they can use to modify the design, because you can have everything green and still it could be a horrible design. So this design evaluator is a very nice feature which you can use to quickly go through as a senior engineer in the company because when your junior engineers will be forwarding you their models, you can go through them in 15 minutes, 20 minutes, half an hour, and give them a lot of nice comments which they can use in their refinement of the analysis.
Now, I had touched upon this in the steel webinar a bit, but I want to just do a small recap of that. And that is that while we can work in the locked model as well, as far as the design of connections is concerned, but we can also work with the unlocked model. And to do that, we need to do a few things before we unlock the model. And by that, what I mean is that we need to tell Comosys to go through all the load combinations and find the maximum forces in the beams and in the horizontal braces and in the vertical braces and in the trusses and in the purlins, etc., and actually assign those maxima as a ratio of their capacity. So if it's a vertical brace, for instance, it'll be a ratio of its axial capacity. If it's a beam, it will be a ratio of its shear capacity. If it's a truss element, it will be a ratio of its axial capacity once again. And then there are those elements which we design according to the full capacity anyways, things like moment connections and all, but we're not talking about those right now. For other elements like floor beams and trusses and horizontal braces and vertical braces, etc., we basically convert the equivalent forces of all the load combinations into one what we call the capacity ratio. So if I were to, for example, zoom into any one of these beams and double click on one of them, you can see over here that the shear capacity ratio right now is 0, as is the axial capacity ratio. What this basically is telling the program, what it is basically telling you is that right now the Comosys has not converted the results from the analysis into equivalent ratios. Right now there is 0. Now what we can do is, for example, if I were to select this beam and go to this capacity ratio button over here and say assign capacity ratio and press that, it does it immediately, and reopen it, then this time we will see that there is a number over here and there's a number over here as well. And what this is saying is, now the first thing we do is, and a lot of these beams, the shear capacity ratios are actually way below 0.5. They could be like 0.1 or 0.05 even, or 0.2, because sometimes in these long beams the loads are so small that as a percentage of their capacity these numbers turn out to be very small, and that leads to extremely, so just say 1 or 2 bolts, and that doesn't look good in the connection. So we have a rule that when we convert these ratios into equivalent capacity ratios, if they are less than 0.5, we at least convert them into 0.5. So if it turns out to be 0.07, for example, you will see a 0.5 over here, because you don't want to have just one bolt as your design in your design connection. And if it's between 0.5 and 0.6, let's say 0.57, something like that, we convert it into 0.6 and then 0.7 and all that. So we round off to the nearest number and we keep going like that. But and there's also, we go through all the axial forces in the beam and then convert that into the axial capacity ratio. So right now what it has done is it has gone through all the load combinations which were present in the model and found the shear in this beam for all these load combinations. And for each load combination, it has found a shear capacity ratio, and then taken the maximum of those and put it in here. That's what pressing this command basically means. And then after that, you can unlock the model, because then the program can work with these two numbers over here to create the beam connections. Now, if I were to zoom out a bit, I don't necessarily obviously have to work one element at a time. I can select a whole bunch of elements and say assign the capacity ratio, and it will go through all the elements which I have chosen and go through all the load combinations which exist in the model, and then basically assign. So it says computed capacity ratios for each element is set. What it has done is it has gone in, it has found gone through all the combos. If I double click, so this one has been set to be 0.5. The axial capacity ratio is very low. If I double click on this one is set as 0.7. If I go into, say, a vertical bracing, you can see it's 0.859 is pretty high. That's why it also, with the high numbers, it keeps the exact number. in the vertical bracings. Over this one, in this one, it's 0.5. So what it's basically done is it's gone through all the load combinations, and wherever axial load is required, so that would be your vertical bracings and horizontal bracings and your trusses, etc. It has converted them into an axial capacity ratio. And wherever shear forces are dominant, like floor beams, those it converts into a shear capacity ratio. And then as far as the moment connections are concerned, they're always designed according to the full moment capacity, so we don't really need a ratio of 1. We just do it with a ratio of 1. Now, as a general rule, these connections always should be over-designed a bit. You don't want your steel structure failing from the connections. If anything, it should be a ductile failure, and the element should yield or not fail, or at least show excessive deformation before anything happens to the connection. So it's always a good idea to, if your forces are 0.3, they should design it for 0.5 or even more. So this is a good idea to have at least some minimums of 0.5, and then if it's more than that, then that can be accommodated. But one thing you can do is that sometimes we have the same section, so the same section could have different capacity ratios assigned to it because of the loading, but you don't want the connections to turn out differently. What you want is actually so let's say this one has a capacity ratio of 0.7, and this one 0.6, and this one 0.5, and this one 0.4, and then 1.2, but they're all the same section. So what you want to do is actually for all the same sections to be assigned the capacity ratio of the one which carries the maximum load, because in that case you will have a very consistent connections everywhere, rather than having this one getting 6 bolts and this one getting 4 bolts and this one getting 2 bolts. You will have the same connection everywhere for say the IP 160 connection. And for that, what you can do is you can select the elements and go to your capacity ratio and say assign the maximum capacity ratios. What it will do is it will group the selected elements according to their sections, and then find the one which has the maximum capacity ratio, which has just been assigned. So you need to use this command first and then use this one. And when you do that, it will group them together and find the one with the maximum and then assign that maximum to the others. So this is a very useful command which you can use as well. And what that will do is it will lead to a very uniform set of connections throughout your building. One type of nonlinear analysis, which is very common in structural engineering, is the analysis of soils as compression-only springs. Now, foundations have soil beneath them, and this and the foundations can be subjected to, or the structure can be subjected to, lateral loads. And under these lateral loads, we might have an overturning of the foundation. But analyzing for this overturning requires that the soil be modeled as compression only springs, something which is not able to take any tension. So for here, if we look at the load case of earthquake Y, for example, a lot of this area is under tension. There is no stress under the soil because of these loads. Similar would be the case for example, wind in the X direction, or if we were to take some other wind in the Y direction, would be something like this. So you need, and these are load cases. So in the combos, the situation is slightly better because you have the vertical loads as well. But what you do in Comosys is if I were to double click on this supershell, you can go to the settings tab, and here you can see that below the supershell we can give soil springs. Now these springs you can give different springs in the X and Y directions and different in the Z direction. So over here, for example, we have defined 2 springs, soil KH and soil KV. KH are the ones which we use in the X and Y directions to basically keep the foundation stable in the XY movements. But the KV one is the one which is nonlinear, which is the vertical component. And if you were to go to our materials tab, for instance, and we scroll down till we get to the soil KV, we can go and we modify view. We will see that it is elastic compression only type spring, and we can give it a direct subgrade modulus of reaction in your units. And once you do that, and then you run the analysis, Comosys will do a nonlinear analysis for you, and then very easily find you or predict whether there will be any overturning in the soils under the combos. Even under the load cases, but it's obviously the combos which you're interested in. Now, in Comosys, you can either do the analysis like on the screen in which you actually model the superstructure as well, and then the loading comes on the superstructure and it gets transferred to the soil. Or what you can also do is you can fix these points and then find the reactions and then transfer the reactions to another model where you have the supershell, the foundation supershell weighting, and the loads are transferred to these points, and then you can do that analysis separately depending on how you want to approach, whether you want to include the soil structure interaction or not. But it's a very useful feature which is usually not available in many programs, or they try to keep it separate. But in Comosys, we've provided this ability to analyze soil as compression only springs within the program, and that's going to be very beneficial for you.
Now let's move on to this example over here. This is a little very simple truss. We have loaded it with about 1800 kilonewtons in the middle. And the only novel thing about it is that instead of doing a normal classical linear analysis, what we want to do is do a nonlinear analysis in which the material is bilinear. So the material has a stiffness up to a certain point, and then it softens up and goes sideways. And obviously, when it crosses that limit, it crosses that yield point, if you will, then the deflections will start to grow rapidly because it will be a much softer material. And what we've done for that is we've assigned to it a material called steel bilinear, and you can define these materials in Comosys separately. So it's over here, and you can define their yield strains and their hardening factors, etc. And once you have and you can define it to be a uniaxial material or with the type of bilinear. And once you do that, you can assign that to truss members, for example. And once you have that, then you can run the analysis and find out about the results. Now, in this case, what I've done is if I go to this create edit analysis cases, I've created a nonlinear static case, and I've told it to divide it into 10 steps. So the load of 1800 kilonewtons will be applied in 10 intermediate steps according to these settings. And when we do that, let's say if I went into this, if I selected this joint and I went to my element output tables over here, I can select the joint frame output. And here, if I select the analysis case to be the nonlinear one, which I just did, now immediately it will show you the result at the end of the analysis. So it is showing you a certain number for the vertical, but what you need is the entire history. So if you select this one, which says response history, it will then give you the results at each of the 10 steps. So so this load of 1800 was divided into 10 parts. So it went from, so this is the result of 180 kilonewtons. Then this is 360, and this you keep adding 180 every single time. So if I plot that curve, and I say I want to plot the displacements of the selected node, and I want to say the U3 displacement, which is the vertical one, and I say OK, you can see on the screen that it went linearly all the way to about half the load, so about 900 kilonewtons. It went linearly, but then it started softening, and it kept the softening kept on increasing as well. And at the full load, had we done a normal linear analysis, it would have been something like maybe something like about 50 millimeters, about 5 centimeters the deflection would have been. But with the full nonlinear analysis, we see that the truss actually goes all the way to about 20 centimeters because it really softens up after that. One final example before we wrap this up, and this is a preheater tower, as some of you would know who are in the cement industry. These preheater towers are very common, and they're very complicated structures, considering the fact that the equipment which runs through them is highly complicated, and there's a lot of different loading conditions. Now, let's say we wanted to do, we don't want to do a response spectrum analysis, but we wanted to do a time history analysis on this. Obviously, I personally prefer to do the response spectrum analysis in most cases because they are much easier to deal with, and they create much less clutter. And one response spectrum can actually cover dozens of time history analyses, because if you select a particular time history, you would need to be very careful because it might not represent the full spectrum of that area. So theoretically also you would need to at least consider maybe 20-30 different time histories and ensure that they are equivalent to the response spectrum of your area and your site. And that's a very hard task, and also considering that doing a full time history analysis itself is quite challenging in many ways as well. But anyway, getting down to what we have at hand, what I've done is, so what we do is basically you start off with the time history function, so you can create and edit time functions and ground motions. So here I've created the El Centro North ground motion. Some of these ground motions are available on the internet. And if you modify and view that, you can see that this is it lasts for about 30 seconds, the shaking, and you can give it a name, and you can import it from a file and all that. And once you have that, you move on to your next step. And that next step is you go to your menu over here once again, and you go to this create, edit, load cases and combinations. And on the right hand side, you have dynamic load patterns. If you select that, you have the option, you can create a dynamic load pattern again over here. And to this load pattern, you can assign any time series. So we just created this time series of El Centro. So if you can create more than one. And you over here, you give it a name, and then you assign a particular time series to it. And then you say that you want to assign this time series in the X direction. So let's say this earthquake is in the X direction. And you have the time series, you can be given some units and a scale factor, and this will constitute a ground motion excitation, if you will. You also have the option of time varying loads, so you can actually apply particular loads to particular joints if you want as well. But here we're going to do a ground motion excitation. And once you're done with that, then you go to this create and edit analysis cases, where you create this analysis case. And inside you can then select the dynamic load pattern which you just created. If you want to add, you could have created more than one, and these ones will be combined. And you need to tell it what integration method it will use. So you have the option of Newmark integration or Wilson integration, and you can also change the number of steps. So obviously the time series has a certain number of steps, but you can go beyond the time series. So for example, the earthquake lasted for about 30 seconds, but you might want to do the analysis for 40 seconds. So you can have a different number of time steps, and even you can have a different time interval as well to make your job or make the process simpler or whatever. Now, once we run the analysis, let me go to this top floor. This is the joint over here, and the ground has been shaking under the El Centro excitation. And if I were to go to the element joint output, and I select the response history, and over here, once again, the final result is shown. But if I select the response history, I can see the whole thing. And then what I can do is I can say plot to the file. And over here, since I did it in the X direction, I'm going to choose U1, and I'm going to say I want to see the displacement of this top column joint. And I say the units are millimeters, and I say OK. And when I do that, I can see that the excitation of the El Centro earthquake has created a maximum response of about 150 millimeters at the top. And then it started to come down, and this is where the earthquake ended, around 30 seconds. And after that, it's free vibration basically for until the damping will bring it down to zero. So at the top level, we have this deflection of about 150 millimeters in the plus direction. If I were to, for instance, go down to this floor and turn on my joints, for example, and let's see if I can zoom in and select this joint. So this is pretty close to the ground this time. The other one was at the top, and I go back to my joint element output. I select my history, turn it on, and say plot. And this time when we plot it, we will see it's a more violent shaking actually, because over here it's much stiffer near the base, and the smaller frequencies, or the higher frequencies I should say, the smaller periods play more of a role, but the overall amount of displacement is much smaller than the top floor, because this is very close to the ground floor. and you can see that it's been shaken more violently as far as the frequencies are concerned, but the total deflection is a lot lesser. So you can do analyses like these and satisfy your curiosity about how the structure is going to behave, and Comosys will help you do those kinds of things as well.
And finally, the marathon is over. With this, we have delivered webinars for all three main areas of Comosys: steel detailing, concrete detailing, and finite element analysis and design. Just like watching these long webinars was a marathon for you, preparing them was a marathon for us. As I said in the beginning, we want these to be like mini trainings for your team. Please watch them all in detail to benefit to the maximum extent. Also, please visit our website at www.proyatech.com. That is Proyatech, Proyatech.com, to find out other details about the software. You can write to us to inquire about any questions which might be bothering you. Our development is continuing at a frantic pace. Very soon, you will get good news of even more features which will increase your productivity even more. Like I said before as well, we will be doing lots of training type webinars with short QA sessions at the end, and we want you and your teams to make full use of them. Please tell your teams to join us regularly, and they will become the best users of Comosys. And Comosys will not let you down. In fact, it'll make your life much easier. With new technology, there are always problems of making the migration from one platform to another. It's called the technology adoption life cycle, basically where the visionaries and the early adopters move before the rest of the crowd and gain advantage over them. Then the main market follows, and eventually even the laggards jump onto the bandwagon. So don't be afraid of being an early adopter. Your willingness to go through some early pains will reward you and your company much more than that. The result is what is important. And of course, we and our resellers are here to help you during the migration stages. Finally, as always, stay safe and see you all soon.